Can you unshare, stop sharing?
And we can also live do the live YouTube telecast also. We can start.
Yeah, thank you. So good morning, everyone. This is the last day of the meeting of the 39th meeting of the ASI, and we are in the plenary session 3. And this plenary session is dedicated to star formation, galaxies, and ISM. And we have 3 talks lined up, half an hour each. The first one is by Kanak Saha of IUCAA, Pune, and he'll be talking on the AstroSat detection of Lyman continuum photons from a galaxy at z equals 1.42. So Kanak, you have 30 minutes. So let's have 25 minutes of talk and 5 minutes for questions. So I will warn you at about 22 minutes. Can you share the screen? Yeah, make it full screen. Go ahead.
Thanks, Annapurni. Good morning to everyone. I sincerely thank the Astronomical Society of India to inviting me for giving this talk. So in this talk, I will present our the recent work that we have done with AstroSat and a bit more that we've been doing right now. So in the first few part of this talk, I will give the AstroSat observation and the analysis of the data, and then I'll try to motivate for the subject, that is the detection of the Lyman continuum photons from a high redshift galaxy. Okay, so as you know, the work that we've done is concerning the deep field, and just for in the layman terms, the deep field is basically a blank field of the sky in which there is no bright stars, because as you do not want any bright star to contaminate, because the idea of the deep field is to look deep into the space, and in some sense you want to explore the fainter and fainter objects in the sky, and Hubble deep field is an excellent example of one such deep field, and which have actually almost revolutionized our understanding of the galaxy formation and the galaxy evolution. So there are several. So in some sense, basically, we want to look into the past, because you go to fainter and then farther and farther away. So there are various motivations one can have to study the deep field. 2 of the motivations which I like and I want to present here is that as you know, the galaxy the observed galaxy populations follows a kind of luminosity function, and the luminosity function, the interesting part is the fainter side. Okay, the fainter side, the slope, which is like alpha, is not yet there is no good agreement in some sense, and in the UV this slope is also remain quite uncertain. And in other words, one can the important part also is that as you go into the fainter and fainter side, there are more and more number of galaxies to explore, and that's one of the so the deep field is basically gives you an opportunity to explore this part much better, because the brighter side galaxies are already no, so there is no point in some sense. Unless you want to look into the very fainter features in the bright galaxies, but this is the very important part to me. And then the UV deep field is particularly ideal, because if you have a deep field in far ultraviolet, so they are basically ideal to probing ionizing sources in the redshift region between 1 to 2, which I will explain as we move on. Okay, so these are the 2 main motivations that we would like to pursue. And then these are some of these high redshift galaxies, redshift 11.1, 10, and 7. These are all from the Hubble deep field. Okay, and most of these galaxies are observed in the observed in the infrared. Okay. So this gives you like a nice idea about how the galaxies look. That you go into the high redshift, of course, because of our resolution, the intrinsic difficulty, we cannot like resolve galaxies. But as you go in, come to like lower and lower redshift in some sense, like around redshift 1, the galaxies become clumpy, and this has some relevance to what we will be talking about. So now I'm going to like talk about this AstroSat UV field that we have created. And this was in the ZT phase, and we observed two fields centered around the good south in the southern hemisphere, and each of them had 50 kiloseconds of observation. So the combined should have like something close to the 100 kiloseconds, but the data recovery was not that very good, and we have actually a total of about 62 kiloseconds of observations in this combined area. And both the fields were observed simultaneously in far ultraviolet and near ultraviolet filter of UVIT to set. And these are the F154, or barium fluoride is the filter, centered around 1540 angstrom. And in NUV, the silica filter, which is N242W, and centered around at a wavelength of 2480 angstrom. So what we did is basically we dissected the entire observations into like about 40 orbits, and each orbits we have carried out the pipeline and created an image. And in this image, you can see like we have marked this like the sum of the sources by green, and then as you like go to the next orbit, the positions like changes, and there are like they appear at different location in the field of view. So what we do is basically we take this as a reference image, and then for all the image we basically try to use shift and rotation algorithm and then stack it. And once you stack it, you get a very nice image, like nice in the sense you can see like what do you mean by nice. So so these are some of the highlights that I show. This is from the two fields. So I join the two fields in near ultraviolet, and I'll also do the same thing in the far ultraviolet. And this is what it looks like in one orbit image. It's a good orbit image. So one of them good orbit image is around 1400 seconds. This far ultraviolet and near ultraviolet, as you can see, like we also like to achieve a good astrometric accuracy. We using the HST as a reference, and our astrometric accuracy is around 0.3 arcsecond. And you can see the background. We saw the AstroSat, sorry, HST, and then on top you see the HST, and our UVIT image. You can see good correlation. So about half a pixel to 1 pixel accuracy. And we determine the sky background in various ways using Dowford, using by hand, like putting the boxes around where there is no other sources. And we also like do a bit more sophisticated way of doing the background, where we removed all the 3 sigma sources, and then around 2.5 sigma, 2.8 sigma sources, and that's how until we get a sort of symmetric histogram for the sky background, and then that we consider the background. And we reach like a very fainter background. So this is the AstroSat deep field, the UV deep field in near ultraviolet. This is the part of the image. You can see it looks like this is the 4-color image, which I'll like show in the next page. And this is the Hubble extreme deep field, where also the Muse extreme deep field. These are the candles fields. So there's this is a very popular area of the sky. And this is the image, is a 4-color image, 2 with the HST, in optical, and the 2 with the AstroSat. You can see many faint sources. And this is the important part here, that we reach a 3 sigma detection limit within 1 arcsecond is around 27.9 AV magnitude, whereas in HST, this is 27.4 magnitude only. So we reach with these preliminary observations that we had in the GT phase about half a magnitude deeper than HST. And this is where the detection that I will talk about in AstroSat and then HST. Okay, so there are various science goals that we had. One of the constraining the faint and slope of the luminosity function. Then there are usual star formation activities and the morphology. The one that are like sort of interesting, and then currently that we are sort of like very massively interested are the hunting the reionizing sources. And that's where I'm going to like give you some brief introductions. Many of you already know. So basically, this is the evolutionary history of our universe, and our universe went through different phases. In the early phase, is going through a phase called the recombinations, when all the electrons and the photons recombine, and this recombination was over around 400,000 years, when the universe was 400,000 years old, and which is around redshift of 1100. And then after that, it went through a phase called the dark age, where there were no stars and galaxies and no light. So as the universe like sort of the cool down from these phases, and the gravitational instability start like becoming important, and the first stars and the galaxies start forming, and when they form, they were probably emitting very high the extreme UV photons, and which sort of started reionizing rather the neutral hydrogen gas around. Okay, now and then that's when the reionization phase started, and we live in a fully ionized area. In other words, the most of the matter between the galaxies are sort of ionized, and our aim, or the goal, the question that interests us is what were those sources? Okay, what were the reionizing sources? Okay, what do we know about them? Okay, now it seems like as we talked about the photons that emit the escape is not an easy process. So as you know, like if you have a star forming region, so there will be like sort of like the Storm sphere around it, and the only way like the Lyman continuum photons, or the photons that can ionize in a hydrogen atom, they emit only if there are some holes in the Storm sphere, or the Storm sphere is like the ionization is like so high that the Storm sphere is like only partially not even formed well. So this is one of the currently the popular area where there are holes in the Storm sphere, and then the ionizing photons like leak through this. So there's a cartoon here, and what I'm showing the whole complication part of it, that the Galaxies ISM. So where if there's some photons like makes its path to escape from the ISM of the galaxy, there are CGM, circumgalactic medium, where they can also be absorbed. And even if some of them actually manage to escape, so there are the intergalactic medium between the galaxy and us, and so many of these photons will be absorbed here, and then maybe very few will reach. And this is the IGM transmission curve from Akio Inoue, and you can see like as you go to the higher redshift 5, 4, the IGM transmission like goes down very severely. So the chances that these photons like will be seen are actually very, very low probability. And then this was the current state of these observations of hunting these reionizing sources. And you can see like these are the sources on the x-axis this is redshift. The y-axis we plotted the observed the Lyman continuum photons versus the sort of the ionizing versus the non-ionizing flux. Okay, and these are the green piece and the blueberry galaxies, which are known recently around 2016, 2018. Okay, these are the sort of the Lyman continuum leaking galaxies. These are the compact galaxies, compact local starburst galaxies. And then also like using cake, there are like the Steidel et al. Shown about a dozen galaxies around redshift 3. So the entire range of redshift between like around 0.4 to around 3-ish where like remain empty. And another important part is the most of these sources that were detected, they have rest frame wavelength is around 900 angstrom. So we do the hunting of this, like the searching for this Lyman continuum liquors using our photometric based detection, and we say that like the galaxy that will emit, it's like the light whose wavelength is like falls within, sorry, the light which falls within this like sort of like a band pass of the, imagine this can be an AstroSat the filter or the far ultraviolet, which is 1300 to 1800 angstrom. And if the light here has a wavelength which is less than like 912 angstrom, then this will be considered as a credible Lyman continuum liquors. And in particularly in our field, that any sources in FUV at redshift greater than 0.97 will be a RESPEM, will be considered as a Lyman continuum. And the Lyman limit is basically 1.z times the 912. And in this case, which we're talking about, is around 2207 angstrom, which is much below the radar side cutoff of the filter. So we have the first detection at redshift 1.42. This was published in Nature Astronomy last year. And there are a lot of efforts also were in other parts of the world to catch those ionizing photons. And for example, there were like large HST program to look for the redshift deserted area to look for those objects. So this is the galaxy which we call the first one in the AstroSat deep field, the AUDFA01 at redshift 1.42. And this is how the galaxy looks like in far ultraviolet, and this is detected with a signal to noise of 3.2 only. And this is with but with the NUV at the simultaneous location, it has a redshift, sorry, it has a signal to noise of 10 with much better detection. So this is the simultaneous detection in some sense. But the important part is the detection in the far ultraviolet. Now, of course, like we look for these galaxies very systematically in the thing in our field of view, and the question is like whether this was a fluke discovery. So we actually to say that its answer is no, and we look for around 1517 galaxies with spectroscopic redshift with the non-zero and positive simultaneous presence of the H alpha O3 and H beta fluxes. This gave us around 942 galaxies from redshift 1.1 to 1.5. This is a nice range. And of these, around 38 galaxies are in Hubble extreme deep field. For us, for some reason, I actually try to focus on that. So this is the galaxy that we're talking about. And so we did a thorough search of the studied about 38 galaxies. In this, only the clean with the signal to noise greater than 2 qualified, and this is with a high equivalent width. This galaxy is also clumpy, so this is for the first time, because as I told you, the most of the galaxies on local redshift are the green peas and the blueberries, which are compact galaxies. And these galaxies are 4 clumps, 3 bright and 1 fainter. And many of the galaxies in this redshift range, which is redshift of 1.1 to 2, are actually clumpy. So this gives hope that that we can actually look for the clumpy galaxies for the sources as well. And this is where also the cosmic star formation rate had its peak. So this is an interesting the area where we should detect more and more such galaxies, perhaps. And there was a lot of the groundwork to basically qualify, because the part is that how do you know all these 4 clumps are part of the galaxy, and also they belong to at the same redshift. So we first did this is the photo Z determination, okay, and we did a SED modeling to determine the photo Z. And in this, we were not satisfied with the clump 2. Then we look for the HST GRISM data, in which we have the GRISM from the 3D HST, and we look for we extracted spectra on each of these clumps, and it was a bit of a tedious task, and this was done nicely by Abhishek, also who was my postdoc here. And we can see that from all the clumps, we have the spectra in H alpha, and we have a redshift around 1.4. So this is we are safe. So all the clumps are the same redshift. So now after the AstroSat, we have a one detection here. So we are hoping like no more and more such detection would come. And we did like also sort of the broadband ACD modeling all the way from far ultraviolet to like near Earth. And we have these galaxies having a star formation rate around 55 solar mass per year. It's a low mass galaxy and also sort of low metallicity. But if you look at the AstroSat flux, we are not able to explain with the normal ACD modeling. So we look for the BPAS, the binary stellar population modeling with that. And what we found that we need a low column density of the H1 and low extinction in this region to explain the AstroSat flux. Once we have this AstroSat, the observations were sort of explained with a model. So now we have a model, ACD model. We wanted to like look for the escape fractions, like how many photons actually escape from the galaxy. So the number of photons that we couldn't escape, that like we come from the KSB recombination. This is the standard stuff from the Osterbrook book. So which is in terms of H alpha luminosity is around 7.22 to the 11th. This H alpha luminosity, we have a very good detection from HST grism. And then the number of photons that escape the galaxy that are we actually use the far ultraviolet flux, okay, in FUV, and we also calculate the total number of photons. And then we use the IGM, the opacity, and we estimate the escape fraction very neatly, which is around 0.2. Okay, if you consider the median value of the IGM, the opacity, then it's like 0.25. We also
you have 3 more minutes.
Yeah, we also like estimate the escape fraction using the standard procedure in which we do the ratio of the ionizing flux observed and then the ratio of the ionizing to non-ionizing flux, the intrinsic, and using the internal extinction and an IGM. So this basically takes into account the IGM and the internal extinction, and then this ratio we use from our BPAS modeling. Okay, and this is the distribution we get. So from this the first method, and is the second method, and we see that at least 20% of the Lyman continuum photon escape this galaxy, which is a good sign. And this has a rest-frame wavelength is around 600 angstroms, and as you can see, like this is the high mass stars, the BPAS modeling, the modeling. Here, this part, like around 600, you have a one observed data points which can like give a constraint this like the models. Like, right now, there are no observations which can constrain these models like the slope of it. So we are also like doing quite a bit of extensive work. We have already found around 300 out of like 500 sources from by combining the muse, and this is the result is ongoing. And also in the future, we are looking for this combined field. These are the field for which we have like detailed observations now, and we are actually also combining the data. And this part here, this is going to be the combined of all. We'll have the AstroSat, the ultra UV deep field, and this will be like I think very useful for detecting further. And these are the team members which contributed in very significantly in this publication. And thank you for attention. I'll stop here if there is any question.
Thanks, Kanak. You're stopped well within time. Thank you. So open for questions and comments. Haven't seen anything in a chat so far. Oh yeah, Koshi has a question. Koshi, go ahead. Someone has to give him access to unmute him.
Hi, Kanak.
Yes.
Nice talk. I have a basic question, basically. The source which you detected, so can it be, did you rule out the chance that it's a background galaxy as well? Like it's only bright in UV, but your optical spectroscopy redshift basically coming from the foreground object?
Yes. I think we have a detailed page. As you can see, this part, the business in this part of the detection is like very tricky. Many of the sources that we have thought about Lyman continuum they were later saying that, okay, no, we have a contamination. So we actually do a detailed background, so if this could be a background galaxy, sorry, background is it's not, but this main important is the foreground.
Yeah, but okay. what I mean is a lensed galaxy, whether this is a galaxy lensed by a foreground source.
So if there is a foreground galaxy, so yeah, there was a question from the referee also in in that context. If there is a foreground galaxy, we would see, it seems like which is shine in FUV, but then it should have some H alpha, which is coming from the FUV flux. And then we show that it should be detected in MUs. But okay. There were no detection in the MUs with this.
Okay, yeah, thank you.
That's how we answered
this. Indulekha, next.
I was just wondering if we took the SED of the 30 door region, subjected it to redshift and appropriate extinction, what would we get if we back modeled it?
30 door, what was that?
This is the nearest starburst region.
Okay, yeah, 30 doors, okay. So can you repeat the question once more? So if we have...
You take the spectral observations on
right.
30, redshift it, then put in the appropriate extinction, then back model it, to find out, what you will get, using the same kind of models that were used here.
So when you just want to just shift in the redshift.
And subject it to extinction, and then
because the stellar population will have to be considered change, right? When you do redshift, the stellar population would be different.
No, what I wanted to check was, you have this near object and you have its spectrum. Yeah. Now you are taking it to that redshift, putting it through the appropriate extinction, and then using the stellar population synthesis models to get back the original spectrum.
What do you gain by that?
I'm not sure what I want to...
What I wanted to... Okay. Supposing the galaxy which is being observed is a starburst type object.
Yeah.
How would the transformed spectrum match with the spectrum observed for your galaxy?
Maybe we should discuss it later.
Yes, I think we can talk about this, but I'm not very sure. I need to understand, because the green peas are also local, but we never do that. Yeah, but I think we can talk to you later.
Yeah. Sandeep Katare.
Yeah, so nice to connect. So I had this question so in the redshift range where you detect this source, so theoretically, is there any estimate how many sources we expect? Is there any theoretical estimation?
No, because the answer is no, because right now this is the state of the detection. Okay, these are about around 10-ish galaxies, and these are around 12. So we do not know for answer your question, we need to know what is called the luminosity function of the Lyman continuum leaking sources. So unless you construct that, I don't think it will be possible to say at what redshift, how many of those sources you would expect. That's what I would do.
Thanks.
But yeah, but more and more, if those are detection, we should be able in a position to construct a luminosity function for that.
Yeah, I don't think there are any more questions and no questions on chat. So let's thank Kanak for a very interesting talk. Thank you, Kanak. So we'll have the next talk now by Liton Majumdar from NICER Bhubaneswar. He'll be talking about, the title is From Molecular Clouds to Planetary Systems, a New Era of ALMA and JWST. Liton, you have 13 minutes. So 25 minutes of talk and 5 minutes of discussion. So I'll give you a warning at about 22 minutes.
Yeah. Thank you. So I'm audible, right?
Yeah, you are audible. We can see your screen as well. Go ahead.
Okay. So first of all, I would like to thank the organizer, especially Professor Nandita Srivastava, Professor Oja, for inviting me to give this plenary talk. So today I will give a talk on the journey of volatiles, mostly the molecules from protoplanetary disks to exoplanets. So this is the work that I'm doing here at NISED. My group is relatively new with a few PhD students and postdoc and MS students. And this work is done in collaboration with several international colleagues. So to give you a brief idea of what we are doing, if we really need to understand the journey of molecules from planet-forming disks to exoplanets, we really need to understand the stages of low-mass star and planet formation. So as we know, stars form in over-dense region in the interstellar medium, which is basically this stage A, which is often referred to as molecular clouds. Clouds mostly consist of gas, but approximately 1% of the mass of the cloud is in the form of sub-micron-sized dust particles, right? So initially, these dust particles composed of silicates and carbonaceous materials, and these dust grains can become also coated with, icy mantles of more volatile species, which have a profound impact on the chemical evolution of star and planet formation. So some dense cores can also become dense enough that they can begin to collapse and overcoming the turbulence, thermal and magnetic pressures. And cores that failed, or I would say the cores that are fated to collapse are referred to as the prestellar core, right? And this collapse is initially isothermal and somewhat asymmetrical due to preservation of cloud angular momentum, which is basically represented as the figure 1b. But when collapse proceeds, the center of the collapsing core becomes optically thick and heats up, and a photostar has formed, right? So which is basically the stage 1c. And now during the photostellar stage, the central photostar continues to accrete mass from the surrounding cloud core. As you can see here, so it is basically accreting material from the core. So within the envelope, but in the envelope, the temperature and density also increases toward the center due to stellar heating. To preserve the angular momentum, some of the accreting material spreads out into the disk, which is eventually serves and with time it eventually forms the circumstellar disk. Now, so this is the disk where we expected to have planet formation, and most of the planet. So we have seen a lot of planet hosting disk with various telescopes like various interferometers like ALMA or NOEMA. So the obvious question to ask: how does the composition of the disk get incorporated into forming planets? So you are forming the planets here. So we should try to understand how does this composition of the disk get incorporated into forming planets, and also how do the physical properties of the disk influence the outcome of the planet formation. So not only the physics, but associated chemistry also has the impact on the on the composition of the newly born planet. So we really need to understand that. So in order to do that, we really need to think what is the fourth stage, which is basically the protoplanetary disk. And as I said, it has a strong density and temperature structure, and the density and temperature is changing across the disk. So so here is your central star, and if you go inside the disk, then your density is increasing, and your also temperature is increasing, and that has a strong impact on formation and evolution of various type of molecules. Let's say you have CO. So CO is in form of ice in the outer part of the disk, and when temperature increases, CO ice will dissolve, and you will have CO in the gas. Okay. So and if you form a planet in this inside of CO snowline, so that will have a different carbon to oxygen ratio in the atmosphere of that particular planet. So same thing, like if you go very close to the star, then you will have water. And if water is in very close to star, your water is in form of ice, and when temperature increases, it will dissolve. So if you form a planet here, then you will have different oxygen to carbon ratio, because most of your water is in form of the gas. So the whole idea is your density and temperature structure continuously changing the composition of planet forming disk, and that has a strong role to play in the atmosphere of various exoplanets that you observe. And this is what we also have seen with ALMA. So this is basically, there's 3 different disks, and we can clearly see. So these are the C80 no image, and these are the dust continuum images. So we can clearly see the structure of different molecular emissions, right? So, and we often use N2H plus as a tracer of CO snow line, where is, so that decide where CO is frozen or CO is in the gas. So you can see the concentrated ring inside, so which is basically telling you CO is in the gas phase, and here the N2H plus is basically is weak. So that shows, like, if you have a CO in the gas, you can destroy N2H plus, and by that you can trace where is your CO snow line in this type of planet forming disk. So we can often define this region as chemical rings. So as I mentioned, you have your star here, and when you go far away from the star, then most of your CO and nitrogen is in form of ice. That's obvious. And as a result, if you observe if you observe CO in this region, then you will only see very faint emissions from CO, because most of your CO is in form of ice. And in this region, so like now when you go close to the star, then your temperature is increasing, and the first material, which is N2, will, because the desorption temperature of N2 is much lower, which is around 17 Kelvin. So N2 comes to the gas phase, and still your CO is in the ice. Okay. Now, if you go further in, then you will see CO is in the gas and N2 is in the gas as well. So if you form planet at different location, from the star, then you will have different carbon to oxygen, different nitrogen to oxygen ratio. So that has a big role to play as well in the atmosphere of various exoplanets that we see. So if we really want to summarize this, then we can, as I mentioned, if we try to look at the chemical structure for various volatiles, like by volatiles I mean molecules with low desorption temperatures. So you can see the depending on the various snow lines, nitrogen, CO, CO2, ammonia, and water. These are the basic ingredients which controls carbon, oxygen, nitrogen budget for various planets, has a strong role to play in the emerging C2O ratio. So when you look at the gas phase carbon to oxygen ratio, which is basically around the order of 1, when most of your nitrogen and CO is in the inside of your ice line. But as you're going in, your C2O ratio in gas phase is going down, right? And also your C2O ratio in the ice is increasing. So this evolving scenario of carbon to oxygen ratio has a big role to play for exoplanet atmosphere. So what we did, we looked at the composition of various photoplanetary disks, and as I mentioned, now we have the access to the ALMA images for various photoplanetary disks, and we know exactly their source parameters, their density, temperature from their excitation condition. And then based on that, we can model the temperature and density structure using so-called disk physical model. And we can use that disk physical model to study the composition when the planet is forming inside a disk of gas and ice, right? And this disk of gas and ice is often get the material from the initial cloud as well, like whether you have inherited some fraction of material from the molecular cloud. So that possibility is also we have considered. And based on that, then you generate the abundances for various molecules, and you use ready-to transfer model, either in LTE or non-LTE, and you generate emissions. And you compare emissions with the observed emissions coming from telescope like interferometers like ALMA. So by that, you can really understand where and how different type of molecules are forming at various locations of planet forming disk. So we looked at the one of the T-Tauri disk, and we look at the physical structure of the disk first. So this is the density structure, as I mentioned. This is the temperature structure, and this is the UV field. And we looked at the basic ingredients which controls the carbon, oxygen, nitrogen budget for planetary atmosphere. So this is, we will start with N2, then this is CO, and this is CO2, this is ammonia, and this is water. So clearly from this plot, you can see water is available in the gas phase only very close to the central star. So this is the last molecule that you can expect to have in the gas phase. And you can see very, ring structure of N2. N2 is not observable in sub-millimeter, but you can track N2 with ions like N2H. But what we can see, N2 is spread across the disk. For CO, we can also see a ring-like structure, because in the outer part of the disk, CO is frozen, then you are going inside, then your CO is coming in the gas phase, and that's the reason why we see chemical rings of CO when we observe disk with ALMA. For CO2, as I mentioned, the desorption temperature of CO2 is much higher than CO. So you expect CO2 is only available around this region, not in the outer part. And same thing is for nitrogen. So why this is because it controls the composition of the planet that will form inside this. So if you form a planet, let's consider if you form a planet here, without part of the disk, then you might have CO. Most of this your CO is frozen, right? Because of its ice line. So same thing we can discuss analogy based on the form location of these molecules across photoplanetary disk. Okay, so as I mentioned, so it is important to understand the composition of the disk, because they dictate the composition of exoplanet atmosphere. And we have now observed more than 4,000 exoplanets with various type of techniques, going from transit to radial velocity, microlensing to imaging. And the one common thing that we observe is all these exoplanets have completely different type of atmosphere. So that atmosphere is so diverse, and their the mass and their temperature structure is also different to each other. So if you really wanted to link the atmosphere of exoplanets that we observe, then we have to link it with the formation location that I mentioned earlier, right? Then why we should care about this atmosphere of this exoplanet? Because in most cases, for most of the exoplanets, so we only have handled to the basic properties of exoplanet, like only we know their mass and radius in most cases. If the exoplanet is close to us, then we can measure the spectra of the exoplanet atmosphere. By interpreting the spectra, we can constrain the atmospheric chemistry, formation history, and also the habitability condition. So one of the biggest thing for exoplanet hunting is hunt for extraterrestrial life. So the extraterrestrial life must proceed by the detection of biosignature gases for exoplanet atmosphere. And now whether a gas is robust biosignatures depends strongly on the atmosphere it is embedded in. So the take-home message is, if we, in most cases for exoplanet atmosphere, for various exoplanets, we have access to the mass and radius. we know the spectra for a handful of planets through various observations like JWST. And by modeling the atmosphere of those exoplanets, we can understand what type of atmospheric chemistry is going on such exoplanets. And also by comparing with the disk model that I mentioned, we can also link the atmosphere of exoplanets with their formation conditions. So, how we can generate this synthetic spectrum? So recently at NICER, we developed forward modeling methods, which is to generate the synthetic spectrum for exoplanets. So which is basically based on various initial parameters like temperature pressure profile. In most cases, this temperature pressure profile are generated from very, based on the observed parameters for various exoplanets. Then we also need stellar radiation spectra. We also need chemical network and initial composition for those exoplanets. So in future, when you have the theoretical synthetic spectrum for various exoplanets, that can be also verified with upcoming telescopes, space telescope and ground-based telescope, like whether those exoplanets really have any biosignatures or features like water to observe with observe in the future. So how one can observe the spectra from the atmosphere of those exoplanets? So one of the most used technique in this field is transit spectroscopy. So if we observe a planet by transit method, then we should observe a dip in starlight when the planet comes in the view, right? So this is basically the transit depth. And now, due to Rayleigh scattering, we can see the scattered light at shorter wavelength, and that can be used to understand the composition of various planets. So here I have shown how absorption law due to some chemicals also increase in terms of their opacity at different wavelengths. So as I mentioned, when we observe exoplanets through transit spectroscopy due to Rayleigh scattering, we can see the changes in the wavelength, and that change can be often attributed to various chemicals that is present in the atmosphere of such exoplanets. So this is the fundamental technique that is used to understand the composition of various exoplanets known so far. So recently, we looked into the atmosphere of one of the super-Earth planet called 55C and CE. We explored the chemistry and observability of nitrogen-dominating atmosphere of this particular ultra-short period super-Earth, for which we know the mass is around 8 Earth mass. The radius is 2 Earth radius. The orbital period is very small, 18 hours, and the temperature is around 2000 Kelvin, and the distance from the sun to planet is around 0.0 AU. So what we looked at the composition of this particular exoplanet and try to understand whether is there any future possibility to observe different atmospheric gases from this particular exoplanet. So for that, recently, as I mentioned, we developed a 1D photochemistry and readily transfer model called photoreference NICER, which has following ingredients in it. So it has a plane parallel 1D model. It has the atmosphere is divided in several grids. To run the model, we need initial conditions and chemical network, which is mostly the combustion chemistry or atmospheric chemistry network. And we know their production rate and loss rate at different reactions for any species we considered in the model. We also have, as we know, we also have the transfer of materials from one grid to another, right? So using these parameters, we can solve the continuity equation in 1D, which is basically which gives you the mixing ratios of any particular species in the atmosphere of exoplanet. With respect to the production rate, loss rate, and ingoing and outgoing flux, as I mentioned. And when we have the mixing ratios, we can also solve the radiative transfer to get the spectrum, the observable signature for that particular exoplanet. So once the mixing ratio is available to us, what we did, we we can calculate the optical depth and also the transmitted intensity at different frequencies using a simple radiative transfer method, which is often linked to the opacity of individual molecular lines. So with all ingredients that I mentioned, we can generate the plots for how the mixing ratio of individual molecule, like let's say AC and CN, changes with respect to altitudes. And this is the mixing ratios of, or you can think this is the concentration of individual molecule with respect to altitude. And we also have the tools to understand how different molecules are formed and destroyed in the atmosphere of this type of exoplanet. So, so as I mentioned here, I have shown the mixing ratio plot for ACN and CN, and we can clearly see a peak of ACN around the pressure of 10⁻⁴. But for ACN, the mixing ratio plot is a bit complicated. So why this is happening? So we can also track down individual chemistry, because we can plot the formation of these molecules, formation and destruction of these molecules with respect to pressure. So for reactions involving ACN, we can see the prominent reaction, because ACN mostly formed through the photodissociation of ACN to ACN. Then there are reactions by which you can form ACN from CS3CN, and so on and so forth. For CN also, same thing. We can also study why the chemistry, how and why chemistry is playing a role with respect to different altitude of the atmosphere of such exoplanet.
You have 3 more minutes.
Yeah. So so when you have access to these mixing ratios, we can generate the synthetic transmission spectrum that I mentioned based on the required spectral resolution. And so this is the transit depth. Then we can also generate the emission spectrum, which is, if we assume the planet is hot enough, then we can also see the the black body spectrum from such planet. Probably I will go to the one of the plots that is important to understand here. So we looked at the transmission spectrum for this particular planet, 55 CNC, under different C2 ratio. As I mentioned, the C2 ratio is extremely important depending on where is your planet is forming. And what you can clearly see for higher C2 ratio, like, so you can think the carbon-rich atmosphere are defined by the shape of the ACN and also the shape of CN. So for this particular exoplanet, what we can see, for high C2 ratio, we can easily observe ACN and CN from this exoplanet. But when you have low C2 ratio, then it is dominated by the absorption of water. Okay, so you can see the absorption features of water. So for this particular exoplanet, what we learned is when you have the high carbon budget in the atmosphere supplied from the disk, then we can see a lot of ACN and CN. And if we have low carbon to oxygen, if we assume the planet is formed further away, then we have most of the water we can see most of the water through absorption. So same thing, so if we can study the emission, then we can also see in the emission spectrum for this particular exoplanet, for carbon rich, it is mostly dominated by ACN and CN. And for C2 ratio 1 has a general shape defined by ACN and H2. And low C2 ratio is mostly dominated by absorption of the water feature and CO2 features. So, and that corresponds to, and also we tested how this is, changes with respect to different nitrogen and oxygen ratios. So, so this is one of the plot where we have looked into the parameter space of nitrogen to oxygen ratio and carbon to oxygen ratio for this exoplanet. And what we understand in general for most of the changes around C2 ratio 1. So this is where the atmosphere is moving from carbon dominated to oxygen dominated region. CO is mostly constant throughout the C2 ratio, as it is dependent on the both carbon and oxygen element. In the upper atmosphere of this particular exoplanet, most of the molecules have lower abundance as the stellar radiation and hence more photodissociation. So photodissociation plays a role in destroying most of the molecules in the upper atmosphere. In the lower atmosphere, molecules are relatively more stable and due to lower thermal dissociation, we can see higher abundance. And as expected, all the carbon-bearing species show increase in C2O ratio as it is increased. So in summary, so as I mentioned, a relation between formation condition of exoplanet and their atmosphere could be drawn, although it's not very direct. So if we have access to the modeling tools that I mentioned for photoplanetary disk, we can link where the planet was formed, and then we can link to its current location based on the atmospheric composition of this exoplanet. We can also generate the synthetic transmission and emission spectrum that we can observe with various state-of-the-art telescopes, upcoming space telescope as well. And we are also doing a lot of studies in the directions on exoplanet atmospheric retrievals based on some of the archival HST archival data. And we are also not only considering the temperature profile from parametric model, but we are also generating the temperature profile based on radiative convective equilibrium modeling. So what is waiting for us? So as I mentioned, so these are the tools that will be extremely beneficial for the future test program across the globe. So we'll have soon James Webb that will characterize exoplanet atmosphere of various planets, and also there is a dedicated exoplanet atmospheric mission called Ariel soon, and in the future we'll also have TMT telescope from India. Okay, so I will stop here, and I'm happy to take questions from the audience.
Thank you, Liton. Very nice talk. We have some questions coming up. Dibientu, you have raised your hand. Please, you go ahead with your question.
Yeah, hi, Liton. So it's very nice to hear about the new groups that established at NICE, and that's a great talk. I have a question. I'm trying to understand. If you observe the current atmospheric constitution of an exoplanet, does that uniquely constrain the very early protoplanetary disk environment from which the atmosphere formed? As in, if I reverse the question, is there a unique chemical evolutionary pathway from the past to the present exoplanetary atmosphere?
Okay. Yeah. So so yes, I would. To answer that, I would say the relation is not one-to-one. So if we observe all these exoplanet atmosphere are so diverse. Like in most cases, we know we have the access to their measurement of carbon to oxygen ratio. So if we know the carbon to current C2O ratio, and if we can fit to the C2O ratio from the disk atmosphere, the photoplanetary disk, and if we can fit that C2O ratio with the current C2O ratio with the evolving scenario, then only we can link. So there is no one-to-one link. So like by just measuring C2O ratio on one particular exoplanet, we cannot tell, okay, so this exoplanet was formed further away from the disk, or it formed very close to the disk. But what we can do, we can start with, we can run models to generate carbon to oxygen ratio at different location of the disk. And then based on that C2O ratio, if we evolve the atmosphere of exoplanet, and if we fit the spectrum, then from that, through reverse modeling, we can trace the origin. But this is what I said in my here. The relation is not one-to-one, so it needs a bit of modeling, and if the modeling is mostly the reverse modeling. Yeah.
Okay, thank you.
There's a question from Indulekha. Indulekha, go ahead.
Just two questions actually. What complication does dynamical friction migration of the planet cause to this picture? And the other is, we have observed planets around binary systems, as well as I think there was a recent observation of the accretion disk around a binary star system. So does that introduce degeneracies? Like it makes the picture more complicated, but single planet atmosphere, sorry, planet around a single star, will it be degenerate with, can it be degenerated? Double star.
Yeah, so let me first answer your first question. So basically, as I mentioned here in my in the model part, like when you evolve the chemistry for any exoplanet, you need to start with some carbon to oxygen ratio, and so this initial carbon to oxygen ratio, it depends on the disk from where you expect to have your planet formation. So now it depends on you. Like if you assume your core accretion or your planet is formed further away from the water snow line or further away from CO snow line, you will end up with different carbon to oxygen ratio, and then you can run your model based on that. So I cannot tell you exactly whether because our results is mostly limited to for this one particular exoplanet, but in general, there is, as continuing what I said to the Bendu, like the C2 ratio is not, it depends on so many other factors, not only the chemistry, but also the dynamics, as you mentioned. So, and it depends, end of the day, it depends on what you start with, and end of the day, you have to fit the spectrum that is coming from the, facilities like HST. So the answer is yes or no, both. Like we can do together. And for the second part, like whether we have seen scenarios for, if I understood, like binary system. So here we model for planets around single star. Okay, so we haven't looked into the scenario where we have multiple planets, planets around binary stars yet. So in future, probably we can explore, but in that case, we really need to understand also the stellar profile, because that's one of the complicated problems if you consider the, binary star. Yes.
Thank you.
Yeah, thank you. I think there are no more questions or raised hands, and also we are running out of time. So thank you, Liton, for a very interesting talk.
Thank you.
So moving on, we'll have the third talk by Sarita from IST Trivandrum. The talk is titled Star Formation and its Effect on the Surrounding ISM. Sarita?
Yeah. But before Sarita starts, I would just like to announce that we are going to have a group photo at 11 o'clock. So please do not leave and stay on Zoom, and we'll take a group photo. Sarita, please go ahead.
Yeah, thank you. Thank you, Annapurni.
Yeah.
This
Great.
is fine,
go
right?
Yeah, so I will give you a warning 22 minutes, 25 minutes for the 25-minute talk. Give some time for questions. Thank you. Go ahead.
Okay, yeah, thank you. So first I would like to thank the organizers for giving me this opportunity to talk about, sorry, one second. Giving me this opportunity to talk about this theme of star formation and its effect on the surrounding interstellar medium. And so the plan of the talk in short is as follows. I'll talk about the processes in star formation, the process that affect the interstellar medium related to star formations. I'll talk in general about stellar winds, photoionization, and protostellar jets with some examples, as well as triggered star formation. So my work has been made easier by Liton, who has already given you an introduction about the various phases that stars undergo. The molecular clouds are the densest phase of the interstellar medium, and these are inhomogeneous with clumps and cores, and it is within these that the star formation proceeds. The broad sequences through which the LOMA star formation proceeds is shown here and has already been discussed, so I will not be going into it. But in the case of massive star formation, it is expected that because of the high mass of the star, things are expected to be different in the way the formation process occurs. And from an observational perspective, one way to locate the various stages of the star formation process is by looking at the spectral energy distribution, which is shown on the left-hand side here. And these are the various phases. For example, they are generally classified as class 0, class 1, class 2, class 3. This is the earliest phase, and this is where you have the disk in the protostar with the disk in the envelope along with disk wind and outflows. And this is the later stage, protostellar stage, class 2. And one good method of segregating these objects into different classes is by looking at their spectral indices in the mid-infrared regime. And now we know that wherever there is star formation in the interstellar medium, this is always a very active region, and it is riddled with bubbles, shells, pillars, and outflows. And the star formation process itself is very tumultuous, and there are various physical processes that have been invoked to understand this, as well as the role of the initial conditions. What role the initial conditions play in the star formation, that is also under study. So which plays a more important and significant role needs to be understood. The processes that go into picture, for example, are gravity, the turbulence that is observed, the rotation, the magnetic fields. And in the case of massive stars, for example, the mechanism, as I already mentioned, is not very clear, because the massive stars, in the case of massive stars, they reach the main sequence phase and they start emitting photons while still accreting material from the surroundings. Another interesting observation that people now know is that these stars do not form in isolation, and they are mostly formed in clusters. So in the initial earlier stages, how the fragmentation of the clumps happen, which lead to the formation of the clusters, that is also an area that is still under which is under active study. Now, if one looks at the star formation process itself, one of the long-standing problems is that the star formation occurs on is highly inefficient and slow, and the star formation rates, for example, in GMCs is of the order of giant molecular clouds is of the order of few percent, and if one looks at the molecular clouds, the more denser regions, one can think it is of the order of few tenths of percentage. And in fact, and this star formation proceeds on timescales which is much slower than the free fall timescales of the molecular cloud. Because if the star formation had happened then at the free fall timescale, then most of the gas in the Milky Way should have formed stars several gigayears earlier. And in fact, the star formation rate should have been much higher, at least 2 orders of magnitude higher than what is observed. Then, one way to understand this is the effect that stellar feedback has on the interstellar medium itself, because it slows down this entire process. In addition, turbulence has been observed in molecular clouds, and it is everywhere in molecular cloud, GMCs, and even with very small scales. And to understand this turbulence also, one needs to invoke the effect of the feedback. And this is a picture which is towards the quintuplet cluster in H1 to show the tumultuous medium surrounding this cluster. You have the effect of the stellar winds. You have the, for example, the nebula here, which is getting compressed. And then you have this large region, which is very excited and shows a pillar-like structures. So what are the various processes that affect the that affect the interstellar medium? Now, they can be broadly categorized as follows. These processes inject energy, momentum into the interstellar medium. And the first of these is the photoionization, that is the massive OB stars. They ionize the region around interstellar medium surrounding them, and this ionized region can also expand. So this way it can affect the surrounding interstellar medium. Then one has the effect of the stellar winds, the massive stars whose mass is greater than 40 solar masses with effective temperature greater than 25,000 Kelvin. It is found that these affect the interstellar medium, can affect the interstellar medium in a significant way. Then we have the radiation pressure from massive stars. Then we also have the jets and the outflows, because these can, this is the material which is given off in the earliest stages, and these can reach velocities of 10 to 1,000 kilometers per second. These also produce shocks which heat the ISM as well as transfer momentum. And if one looks very closely, it has been found that accretion can also heat up the circumstellar medium because of the heating of dust grains near the protostar, which in turn heats up the gas because of the gas-dust coupling. And if one looks at the evolution of massive stars, because on a large scale, if you have a molecular cloud, then the massive stars as well as the LOMA stars are evolving simultaneously, but the massive stars evolve much, much faster. So while the LOMA stars are still in the earlier evolutionary phases, the massive stars would have, for example, finished even their main sequence sequence phases. So the later evolutionary stages, for example, when they, the most massive ones, they can give off stellar winds, which are the WR stars, which affect the surrounding medium. And finally, the supernova explosions can happen. This I'm talking about the core collapse supernovae. They can cause an explosive transfer of energy and momentum. So if one looks at all these factors or which affect the interstellar medium, one finds that massive stars are a very important role to play in the way in which they affect the surrounding interstellar medium as compared to the LOMA's counterparts. So here is a schematic showing how the O-type stars, the massive stars, affects the surrounding medium. Here is a wind-blown bubble where there is very diffuse medium and which is very hot, and surrounding that you have the compressed H2 region, and you have the PDR beyond that. And as we can see, each of these are excite different kinds of lines or transitions, and one can sample them using those transitions. And finally, you have the cold interstellar medium. Now, when we usually take observations on the sky of different star forming regions, all we get are snapshots. But to understand how these different processes affect the interstellar medium, we need to take the support of simulations. So here, for example, is shown one region, RCW120, where a particular H2 region bubble has been modeled by Howard and others. And here you can see this small region corresponds to the region which is excited by the winds, whereas this is the outer region is mostly because of the shock front expansion of the H2 region. Now these wind-blown bubbles survive, the small grains survive this in the wind-blown region, and therefore you can see that this region is visible in 24 micron as compared to the longer wavelength regions. Now I will also talk about other simulations that have been carried out in order to understand the effect of these processes. And here is an example of a simulation which shows the effect of stellar winds from massive stars, a group of massive stars in turbulent molecular clouds. So what is seen is that, as you can see, the timestamps are given here. This is the column density. What one sees is that there is a rapid clearance in the central region around stars, and it leads to the formation of low density channels through which the hot gas streams out. And most of the cold dense material survives, and it gives rise to these pillar-like structures which point towards these O stars. And this is what they found as the effect of the stellar winds alone from these massive stars. Then how does photoionization also affect? I mean, in comparison to the stellar winds. So this is another set of simulations which was done to show the combined or coupled effect of the photoionization as well as stellar winds. So this is the initial molecular cloud with a group of stars which are formed here, massive stars, and this is the timestamp at identical timestamp, where this simulation takes in only the effect of the photoionization. As one can see, it is on much larger scale, but it still maintains near this. It is able to clear out the region on much larger scale as compared to stellar winds alone. So this is the effect of stellar winds alone. So if one combines the two, this is what one gets, that one is able to clear the surrounding medium surrounding interstellar medium, and the effect from photoionization is much more than those from the winds. And one can also see the filamentary structures here in the cloud, which is ubiquitous and has been observed in many star forming regions. Now, this is one of the study that we had done towards a H2 region complex, and I will just talk about one particular small region here. I will not talk about the entire thing. Here, this was an infrared bubble which we had seen towards this H2 region complex, and this is a broken bubble of the size of 2 parsec, the thickness of about 0.3 parsec, and this is a color composite in for example, in 3.6 micron, the Spitzer wavelength band, the green is 3.6 and the red is the 8 micron emission. As you can see, the 8 micron emission is mostly towards the outer region. The blue is shown, indicates the radio. As one can see, that if one takes now what is giving rise or what is exciting this bubble. So for this, we took profiles and found that at 3.6 micron, for example, there is a candidate which we believe seems to be exciting this. And the interesting thing was that in radio, we observed these pillar-like structures which seem to point towards this young group of faint exciting stars. So we think that this bubble region which has been excited, this is mostly a wind-blown bubble in our probability which has been excited by this cluster of stars which we see at the center. We also had, since we had observations at 2 different wavelength bands, another interesting observation was that the spectral index map towards this region showed negative lower values. Negative values indicating the presence of non-thermal emission. That is, this is a very interesting observation because it would tell us that that the particles can get accelerated in the shock fronts across these bubbles. Now, this star formation, the effect of these processes can be positive or negative. That means there could be the star formation process could be destroyed because the molecular cloud is dissipated, or it could be also be positive in the sense that it could further trigger star formation. And shocks, for example, are believed to play a very important role in this. And when, for example, this schematic here shows how the shock affects a nearby molecular cloud. When a shock front passes through the clump or a molecular cloud, small molecular cloud, it tends to compress it. But even after the shock has passed, there is gas motion in this cloud. And this gas motion can cause gas to clump up, that means the high density regions to become gravitationally unstable, leading to the formation of stars. So we know that, as I mentioned earlier, the star ISM has a lot of shells, bright rimmed clouds and pillars. And for our understanding of the shell-like structures or the bubbles is because of H2 regions, winds and supernovae. And the pillars and globules, for example, can be well explained due to the expansion of H2 regions and from massive stars due to density or inhomogeneities. Now, in terms of a coherent and organized way, these are broadly classified into 2 types of trigger star formation. One is collect and collapse model, and the other is radiation-driven implosion. There is also a cloud-cloud collision which can be which triggers star formation, but I am not discussing that here. So this briefly describes the triggered star formation scenario, where the collect and collapse is internal to the molecular cloud in the sense that the star gives off the UV photons, and this leads to the compression of gas at the edges, and this compression can give rise to further star formation. On the other hand, in radiation-driven implosion, the star is, this is from an external medium. That is, you already have a molecular cloud, and this region is already cleared, and the O star can, due to the radiation from the O star, radiation pressure, there can be this can trigger a collapse towards this region, towards these kind of pillar regions. And now these need not be too separate in the sense, while they are two separate modes of star formation that in the way that we understand, they both can occur during the evolution phase of a single molecular cloud. For example, this is the W3 complex, and here it has been shown that as the cloud evolved initially, for example, it triggered star formation by the collect and collapse model, and as the molecular cloud broke up into more pieces, then one can try to explain the presence of the globules and others through the radiation-driven implosion method. And these are some simulations which are trying to understand the radiation-driven implosion as well as the collect and collapse. So here in this set of simulation, the star is located below here, and this is indicating the timestamp. And due to the radiation pressure initially, this gets more the material is ablated here, and what you are left with is a pillar-like structure or globule-like structure, and which can trigger the formation of stars at this location here. And this is the example of collect and collapse, where this is a molecular cloud, and at the center you have a massive star which can which can give off winds and ionize the surrounding region, which in turn can lead to the formation of gravitationally unstable fragments towards the rim, forming stars, leading to the formation of stars. Now, I will talk about some of the regions that we have studied where we have seen some of these effects. For example, the expansion of H2 region has been studied in, we have found in the star forming region G351.7. Here we used we all know that H2 regions expand, but we wanted to trace this, and for this we used the radio recombination line using GMRT, and we showed that as it is expanding towards the lower density regions, basically towards this direction, as one can see here, the contours here indicate the radio. Towards the lower density regions, they are moving, it is moving faster as indicated by this slide here, and also shown in the schematic. That means the expansion of gas is occurring towards the lower density region, and this is a cometary head, and towards the cometary head you have a number of clumps here. Now, if one looks at this entire region in its entirety, one finds that there is a region which is devoid of emission here, but you have gas here. This is because there is a small cluster of stars here, and it is possible this is the earlier generation which gave off stellar vents and then triggered star formation, because we found a number of clumps here, and these clumps here which are shown here, they are the more active star forming clumps as indicated by this red rectangles here, whereas these are the quiescent clumps which are located far away, and it is possible they will be forming stars soon. And this is where we find stars forming. H2 region is very active, and this is a region which is in an earlier phase of star formation. So this compression or expansion in this direction, it's possible is triggering, has triggered this region to lead to the formation of protostars. Now, we also found another interesting thing is towards this region, we found a non-thermal emission, and we wanted to understand this on large scale. And on large scale, we found, this is the region which I was talking about, the H2 region. On a large scale, we found, now when we imaged at low radio frequency, we found a non-thermal emission which shows a shell-like, broken shell-like structure. And this is this region, as you can see. This is this entire region, this box corresponds to this here. So the red is the radio emission. As you can see, this indicates, and it had spectral indices towards this rim. There are H2 regions plus the spectral indices towards this region. As we increase, as one increases the frequency, we saw that the flux emission goes down towards the rim of this shell, indicating that there's a non-thermal emission towards this shell, whereas the emission towards this region increased, indicating that this is thermal emission from here. So there's a strong possibility that this is a supernova remnant, as you can see, but this is deeply embedded in the molecular cloud. This blue region indicates the cold dust gas emission. And when we looked at this in optical, we found with H-alpha a shell-like structure. So this implies that in this star-forming complex, we found a supernova remnant, and whether the supernova remnant triggered the star formation, or whether there was already a cluster here, and among them the massive stars one of the massive stars evolved and formed a supernova. That we do not know yet. But when we wanted to see what is causing, whether we can find a progenitor to the supernova remnant, we just carried out observations at, we found a Fermi-Lat source here, which is possibly associated, we do not know. But with H1 emission, we found that there is, we found fragments along the shell as well as a protostellar jet, which was very interesting.
3 more minutes, Sarita.
Yeah, thanks. Finally, I will talk a little bit about the effect of protostellar jets, which we are also studying. And this is the protostellar jets are given off from the early phases of low mass and high mass stars. And this has been observed. It's an observed phenomenon. We are still trying to understand what are the mechanisms that drive the outflows, although broadly it is known that to conserve the angular momentum, this kind of outflows must be given. So this is a schematic of a jet, and outside it is entraining material in the form of an outflow. This is a simulation which is showing how the protostellar jet, here the arrows indicate the velocity vectors. So how the protostellar jet is actually driving or affecting the surrounding interstellar medium. Here the color scale indicates the column density, and it is now believed that the turbulence that we see in molecular clouds has to understand this effect of this turbulence, the protostellar jets and outflows are believed to be one of the main cause, because this turbulence is observed in most of the molecular clouds, and there needs to be some mechanism by which this turbulence is continuously replenished, and one candidate for that is the protostellar jets, and they also create shocks at the edges leading to Herbig-Haro objects. So protostellar jets does affect the interstellar medium in multiple ways, but another interesting way in which the effect is that they can also trigger star formation, for example, because, and this has been observed towards the star forming region towards Orion, where it is believed that because of the effect of this outflow, it has triggered the formation of a star. We have also been trying to look at the effect of the acceleration of particles in the shocks, terminal shocks of these protostellar jets, because this is another interesting aspect that we know that there are lots of cosmic rays, but low energy cosmic rays, it was never thought that jets could give rise to them. But now, more recently, it has been found that protostellar jets also have non-thermal emission. And in fact, one of non-thermal emission, both through the presence of the negative spectral indices and radio, as well as the detection of polarized emission. For example, this has been observed in one of the massive protostellar jets. Up to 5 parsec, one has seen the presence of synchrotron emission. And this is because of the shock acceleration of thermal electrons across the shock front. And this is the same protostellar jet, but if one looked at the radio spectral indices, it was found that the spectral indices are of the order of -0.3. But if this, so one way to see, another way to confirm the presence of synchrotron emission is to go to even low radio frequencies and see if we get more negative spectral indices, which is what we had done. And we found that this is the same jet. It is a very large jet, approximately 20 parsec. And we observed this using GMRT and different wave bands. And here VLA is also shown. And we found that for these represents the various lobes of the jet. And for these lobes, we've got very negative spectral indices. This kind of confirms that not only close to the jet, the synchrotron emission is seen, but synchrotron emission is also produced in the Herbig-Haro objects very far off from the jet when the jet interacts with the dense interstellar medium.
So now, can we finish in a minute's time?
Yes. Yeah. I have just a couple of slides. So the effect of the protostellar jet, now where is this the non-thermal emission being produced? So with VLA, very high resolution, Kamenetsky and others, Rodriguez, Kamenetsky and others, they had actually imaged, and this is the spectral index max, which indicates that the non-thermal emission is towards the edge, not only towards the terminal shocks, but also towards the edges where the jet interacts with the ambient medium. And finally, I would like to say that we have been trying to understand this through modeling. Sri Lakshmi, along with Sri Lakshmi, we have been working on some models to understand the radio spectral indices and try to understand them using some simple geometric simulations. So with this, I come to the end of my talk, and the takeaway that I would say are the following: that the stellar feedback is essential to understand the rates and efficiencies of star formation in molecular clouds. The process of this process disturbs the ambient medium in multiple ways, for example, through H2 regions, stellar events from massive stars, supernovae, and protostellar jets. And massive stars among them exert a stronger influence, and these effects can be positive or negative. And in terms of positive, they can trigger further star formation. And an additional way in which they can affect the star formation can affect is to accelerate particles to relativistic energies. And overall, if one wants to see the effects of all these feedback processes, it is very important to try to study them, because they are essential for understanding global star formation in the giant molecular clouds as well as across the galaxy. So thank you for your attention, and I can take questions now.
Yeah, thank you. So Liton has raised his hand. So Liton, go ahead with your question.
Yeah, thanks, Sarita, for your nice talk. So I was just wondering, have you thought of studying the photostellar JWST in your source using any molecular emissions?
Yes, I have done. I have done for the disks with a group. I have been involved in some such observations, and in fact, I had done some simple modeling also using methyl cyanide. But these were mostly when we were looking for disks around O-type stars, because it is very well known that around low mass stars disks exist. But whether disks exist around O-type stars, B-type stars was now to more or less it is kind of confirmed, but we were trying to understand them. And in that context, yes, we had looked at some of the molecular emission from B-type stars around disks.
Okay. And okay, so is there any way you can distinguish jet and outflow in your source?
Okay, so that very often the Kepler, I mean, if you can see the Keplerian motion of the disk, which you can do with molecules, as you suggested just now, you can, if you see this, you see the velocity structure, and if this is kind of Keplerian, then you mostly associate it with a disk. And secondly, the outflow is very large scale. The disk will not be as large scale. So the protostars, protostellar jets and the outflows will be much larger scale. And if you see a structure which is perpendicular to that and kind of and has Keplerian motion, then you can say that's the disk. Alternately, you may not have a large scale outflow, but if you see a Keplerian kind of motion associated with the disk, or then you can say that that is, you mostly associate that with the disk rather than an outflow.
Okay. Okay. Thank you.
Vineet has a question. Go ahead, Vineet.
Hello.
Hello.
Yeah, so thank you for the nice and informative talk. I have one small question. That you have shown in the slide that the outflows and jets triggers the star formation in a kind because of the shock in the nearby clump or clouds.
Yes.
And they are also one of the possible reasons behind the turbulence.
Yes.
And turbulence, in a way, in a kind, it also opposes the collapse of the molecular cloud.
Correct.
So means it is a dual role kind of thing.
Yes.
So how you will quantify or so determine that, I mean, how you will quantify the global star formation rate if the dual role is playing by the outflow jets?
Okay, so I think that is where simulations come in, and they are very important, along with some observations. For example, what are the types of typical dispersions related to turbulence that one sees in the molecular clouds? And then one can try to understand these dispersions associated with protostellar outflows. Okay, and it is, turbulence exists everywhere, even on small scales, but still star formation proceeds. In fact, that is believed to be one of the reasons which is kind of slowing down the star formation process. It is not completely disrupting. So you need to have enough turbulence to slow down the star formation, but not completely stop the entire process. Okay. I hope this clears to some extent.
Okay. Yeah, so are there any observations which shows that which quantifies the effect of turbulence?
There are some observations also. Yes, I can't recollect now, but yes, there are a few where people are trying to, because ultimately you need to quantify them and calibrate them very well to see how much effect the protostellar star is causing to a turbulence. They are not very well, they are trying, but I cannot say that one can say with concretely that this is the only reason, things which are giving rise to turbulence in molecular clouds. I mean the protostars. How much of that turbulence is from protostars is not very clear yet.
Okay. Thank you.
Yeah, thank you, Vineet. There is one question from YouTube. This is posted in the chat. Are protostellar jets energetic enough to be considered sources of galactic cosmic rays?
That is what we are saying. Yes, they could be low energy probably, because we definitely see non-thermal emission here. Synchrotron emission has been seen here. So that is one possibility. that is being propagated now, that yes, they could give rise. But then at least in this case, you need to have strong shocks. In this case, the case I discussed, synchrotron emission has been clearly detected. These are very massive protostellar jets. But one needs a larger sample to be able to quantify this. And in fact, unfortunately, there are only very few sources, protostellar jets, from where non-thermal emission has been observed in radio. But that is also one of the reasons is because it has not been observed as much in radio.
All right, thanks. I think that's all for the questions.
Thank you.
Thank you so much, Sarita, and I thank all the speakers for a very nice talk in this session, and also thank to all the audience and good questions which resulted in good discussion as well. Thank you all. With this, we come to we conclude the plenary session 3. And I think there is an important activity now scheduled. All stay and tune. Yeah. Please go ahead. Yeah.
I think it's the most important activity. I think for a conference to get a group photo at the end. Unfortunately, this is like online this time. So please, if you can manage to turn on your webcam and we can start taking screenshots. Okay, so Crispin and Vinny are showing up in the first. Kanak. Okay, so you have to be patient because there is, at least in my screen, and there are 2 or 3 more volunteers across the VOC who are taking it simultaneously. In my screen, there are 7 groups, so there will be 7 snapshots. So be a bit patient. Keep your windows turned on. Thanks.